Hello, today we are going to learn about physics informed neural networks or PINs in short. Let's break down it together so you can just see how an exciting tool in science and technology. Ready? Let's check it. First off, PINs. What are PINs? So imagine like a smart robot, super smart robot that not only learns from the example but also follows the rules of the universe. What are the rules of the universe? Yeah, you guessed it right. The rules of the physics. Pins are a special kind of neural network which is like a computer brain, but they are different from the other. Like how? Because they use the physics laws, like equations that they describe how waves or heat or any other things, like gravity and extraordinary things in physics, to guide their learning instead of just guessing based on the data, which the traditional machine learning does. They make sure that the answer match science. Pretty neat, right? As we can see here, the traditional neural network only predicts and just we are not reliably saying the answer correctly here. At some context the answer is correct, but after the see, as we can see here, we can observe here, after some point, after this point we can see the answers are not correct. It is it is just crossing the line. But if we, what if we just add the neural network with the equation of this whole physics phenomena? This is basically a swinging of a payload, and this is the equation where it is defined, and we are just replacing the variables with the neural networks, a set of neural networks, and based on this we find the accuracy. This accuracy is so huge and the loss is so negligible, like 10 raised to minus 5. Now let's take an example and we just practically use the pins in the wave function. We will be using one dimensional wave equation. So now let's understand what is a wave equation. The wave function is a function, for example, just consider a element which is just oscillating in one direction. So now we have to only practically make a pins neural network, and we will just find out how accuracy it gives. Now I will just dive down into the code and I will explain you each line of the code in simplest form. So before diving into the code, now the pins we are using here Julia language. So you have to first do the setup for the Julia language. You have to just download it from the internet, Julia, and then you have to install. And after installing it into the your computer, then what you have to just add the paths of the bin folder to your environment variables. We will just import the necessary packages like NeuralPDE, Lux, modeling toolkit, optimization, Optim, and GL. These are the parts of the sets of the mathematical problem. The code defines a one-dimensional wave equation, that is double differentiation of u with respect to time, c square double differentiation of u with respect to x square. Okay, so now we will just import the necessary modules of the Julia language. Now we are just setting a random seed for just set a seed for reproduction. Okay, now with the boundary conditions of u is equal to 0 at x is equal to 0 and x is equal to 1, the initial conditions and initial positions is x bracket x 1 minus x, and the initial velocity is 0, as we can see here in the code. Okay, the domain is defined from x equal to 0 to 1 and t from 0 to 1. The wave speed c is set to 1.0. Okay, the essential defining the physics of the problem using symbolic mathematics. This part of the code defines the neural network to approximate the solution to the wave equation. The network has two inputs x and t, three hidden layers and 20 neurons each, and one output, the predicted value of the u, which is the predicted value of the u. The training uses the BFG optimizer, which is of 1000 iteration. We are using here the 1000 iteration. The network is trained using a pins approach, as so it is an example of pins. So we are using the pins approach, where the loss function includes the terms for the PDE, partial derivative equation itself, and boundary initial conditions. The callback function prints the loss of each iteration and to monitor the progress. So as we can just see here, so let's dive to the next part of the code. Okay, so this part computes both the neural network's prediction and the analytical solution on a fine grid for comparison. The analytical solution is calculated using a Fourier series with 50 terms. Okay, this code creates a grid of points from x from 0 to 1 and t from 0 to 1 with a step size of 0.01, which evaluates both solutions at each point and computes absolute error between them. This allows us to see how well the neural network has learned to approximate the true solution. Okay, now after doing this, this is a visualization part, and it creates the results which we can observe. The statics plot during the static plot comparing the pins solution with the analytical solution at 5 specific times: 0, 0.0, 0.25, 0.5, 0.75 and 1.0, in an animation showing how the waves are evolving at time, comparing the both solution, a heat map, etc. I will be showing you all. Now let's execute the code and just check how much the accuracy goes. So while running this code, you might get some errors, which is general. It is not like you are getting that error. So the major error here you can observe is that module not found, or basically module error. So to overcome that, I will be also commenting a line of code which can just add that modules you are adding to the package of the Julia. Okay, so as we can see here, the first step of our current loss was 0.3. Means if you mathematically calculate the accuracy, it founds to be like 99.7. Okay, basically, so first step is 99.7, and if you just see right now, the loss is very negligible, and at last in the 1000th iteration, the loss is basically in 10 raised to 5 decimals. It is something approximately 3.64 into 10 raised to minus 5. So you can just expect how much accurate the pins works. So now I will just show you the diagrams and what we are just get out of the pins. So basically we have get this animation as I am showing to you. This is a animation where we can see the oscillation, complete oscillation from time t equal to 0 to time t equal to 1. So here we can just observe, see. And this is the heat map of the solution. Hope so you have got the solution which I have explained to you. There might be some point where my explanation would not connected with you. I am improving myself and I am learning everything. Thanks for giving this opportunity to learn a new domain in machine learning, the scientific ML, and I will be surely learning this whether if I get this role or not, but I will surely look ahead and just dive into it.